chair for this talk. And first of all, I will share the screen with you. Okay. Okay, so I hope you can see that Xin Sun received a very prestigious award. This is the New Researcher Award from the Bernoulli Society. So let me say a few words about Xin Sun. So he did his undergraduate studies at Peking University, then got his PhD from MIT. He was working with Scott Sheffield, and then he was a postdoc at Columbia University. Now he's an assistant professor at the University of Pennsylvania. It's amazing to me how many fields of mathematics or probability he mastered and contributed to. So there's one group, SLE, Gaussian free field, random planar maps, Liouville quantum gravity. They are sort of related, but on the top of that, he also had papers on uniform spinning trees and abelian set piles, random matrices. And I've noticed that formally his PhD is from 2017, so just a few years ago. But his list of publications is absolutely amazing, and it starts somewhere in 2012 or 2011. So it looks like 6 years before his formal, his PhD. So that's all I wanted to say in terms of introduction. Obviously, Xin Sun, deserves highly this award, and my congratulations. And I guess we can. I will stop sharing, and I will let Xin Sun take over. For those of you who are concerned with the delay, because we are delayed, according to what I've seen, there is no talk following this. The conference hall is not reserved for another talk. So, Xin Sun, you have as much time as you need to present your talk. And please go.
Okay, thank you, Chris, for the very nice introduction. And thank you, everybody, for coming to my talk. So can you see my screen?
Yes, I can.
Okay, thank you. So today I will talk about quantum Liouville theory on the torus. So I want to start my talk by recall some basic fact from two-dimensional differential geometry. First of all, we have this classification of closed topological surface according to the number of holes. So for example, we have sphere and torus and general genus surfaces. And today I will mainly focus on sphere and torus, but there are some similar stories on heterogeneous surfaces and surfaceless boundaries. And given a topological surface, we can define a smooth metric on the surface to make it a Riemannian manifold. And this metric will induce geometrical concepts like distance, area, and curvature, and so on. And what is the most important concept to us is the notion of conformal equivalence. So two metrics are said to be conformally equivalent if they differ by some local scaling. And here a local scaling can be represented by e to some function on the surface. And in general, this quantum Liouville theory is a one-parameter family of measures defined on every Riemannian manifold. And this measure will be called a Liouville field on this Riemannian manifold. It's defined on the space of functions on the surface. And quantum Liouville theory has two very important transformation rules under. So the first one is under isometry. This one is very natural. It just says that if two Riemannian manifolds are isometric, then the measures are just related by the natural push forward. And the other one is the most important to us. It tells us how the Liouville measure change under this conformal deformation. and it says that it only differs by a constant. And this is also the reason I said that this quantum Liouville field is a measure, but not a probability measure, because we want this condition to hold. And this constant actually has the following form. So here, this delta G is the so-called Laplacian Bertrand operator on the Riemannian manifold. And this number is a so-called determinant Laplacian of this operator. So I will not give the precise definition of the determinant Laplacian in my talk, although it will appear several times, but I will just say that this is a number associated with every Riemannian manifold. And this exponent C here is related with this parameter gamma as follows, and this is called the central charge. So I want to say that the first property of this measure is satisfied by every quantum field theory, and the second one is satisfied by every conformal field theory. And this number C is generally called the central charge of the conformal field theory. Before I go to the mathematical definition of the quantum Liouville theory, I will first give some motivations. So the motivation of Liouville theory comes from two-dimensional quantum gravity. So here, a two-dimensional quantum gravity on a topological surface S, it just means random geometry on the surface. And this is like the dictionary between the physical terms and the mathematical terms. So the most, the first example of quantum gravity would just be the so-called pure quantum gravity, and this means the uniform random geometry. It models the universe without any matters. And in physics, it is also relevant to consider quantum gravity coupled with the so-called conformal matter fields. And this is a natural way of introducing a one-parameter family of random geometries on surfaces. So given a random geometry coming from the quantum gravity, if we condition on the event that it is conformally equivalent to a particular Riemannian manifold, then by definition, this random geometry can be written as follows, where we have this random function phi on S. In a groundbreaking paper by Polyakov, he introduced the quantum Liouville theory and showed that quantum Liouville theory is a conformal field theory. Moreover, he conjectured that this random function coming from quantum gravity, it actually follows the quantum Liouville theory. And suppose this conformal matter here, it has central charge Cm, then this central charge is related to the central charge of the Liouville theory by this magic formula. So here, this magic number 26 is actually the so-called critical dimension for bosonic string theory. So after the introduction of quantum Liouville theory, there are mainly two research directions in theoretical physics about the theory. The first one is naturally the relation between quantum Liouville theory and 2D random geometry. So here, a Liouville quantum gravity is just the random geometry induced by the quantum Liouville theory. And the random parameter maps is a very natural discretization of 2D quantum gravity. Then having these notions, tautologically, we have this vague conjecture that Liouville quantum gravity should be the scaling limit of random parameter maps. So back to 1980s, this conjecture remained vague because the notion of this random geometry is not really well defined. Nevertheless, there are some very strong supporting evidence for this conjecture because people show that people find agreement in certain scaling exponent in these two approaches. So in the LQG direction, there are something called Kizhnik-Polyakov-Zamolodchikov relation. And on the random parameter map side, there are some random matrix techniques. And in any scenarios where the exponent can be computed on both sides, they agree. And on the other direction, so in order to solve the correlation function of the quantum Liouville theory, Polyakov and Zamolodchikov, they realized that conformal symmetry in 2 dimensions, it implies very deep algebraic structure of general to the CFT. And moreover, the quantum Liouville theory is a primary example of 2-dimensional CFT in this aspect. So although the research back to 1980s about quantum Liouville theory remains vague in mathematics, it does lead to a very remarkable progress in probability. first of all, the Liouville quantum gravity and in particular this KPZ relation, it gives very deep prediction on the dimension of certain random planar fractals. The most famous example is Duplantier's derivation of the so-called Brownian non-intersecting exponent. And this is later proved by Lawler, Sherman, Werner via SLE. And in the 2D CFT direction, so Balaev, Polakov, Zamolodchikov, they argue that 2D CFT give very precise description of the scaling limit of 2D statistical physics models. And one of the most famous example is Cardy's formula for the crossing probability of percolation. And this was also proved around 2000 by Smirnov. So, and over the last 2 decades, so there is an ongoing effort in probability, which is to build a probabilistic foundation for the concept of Liouville quantum gravity, scaling limit to random parameter maps, and quantum Liouville theory as a conformal field theory. And the current status is that we have achieved a pretty clear global picture with precise theorems, conjectures, and open questions. And my goal today is to present this picture on both the sphere and torus. So I'm highlighting the torus because a few important points will be clouded if we only focus on the sphere. Okay, so let me start by defining the quantum Liouville theory on the sphere. So in mathematics, there are 2 probabilistic construction of this theory. One is due to Sheffield and Duplantier-Miller-Sheffield. And this is based on the intuition that Liouville quantum gravity is a scaling limit to random parameter maps, and it intensively uses the coupling between SLE and the Liouville quantum gravity. And another approach is due to David Kopanin, Rose, and Vargas, and they mainly follow the idea of constructive field theory. And so with Aru and Huang, we show that these 2 approaches, at least on the sphere, they agree. And today I will mainly follow the DTRV approach, which is the second one, because it readily extends to torus and heterogeneous surfaces. Okay, so the most canonical Riemann manifold with the spherical topology is simply the unit sphere on 3 dimensions. And this is the representation of this unit sphere on this extended complex plane. So here, this metric is the so-called spherical metric. And so one of the fundamental theorems in differential geometry is that given any Riemann manifold with a spherical topology, there exists a diffeomorphism from this abstract Riemann manifold to the this extended complex plane, so that the push forward of this metric is conformally equivalent to the spherical metric. And we call this diffeomorphism the conformal embedding from this Riemann manifold to a complex plane. And we know that this conformal embedding is unique modulo Mobius transformed on the complex plane. So recall the transformation rules of the Liouville field. We know that in order to understand the quantum Liouville theory on this sphere, it suffices to focus on the unit sphere case. So the quantum Liouville sphere has a very simple relation. The quantum Liouville theory has a very simple relation to Gaussian free field. So I will first give the definition of that. So here, the Gaussian free field on the sphere is just a centered Gaussian process on the complex plane whose covariance is given by the green function of the Laplacian operator. So I will say more about the precise definition of Gaussian free field in the next slides. For now, I just want to emphasize that the Gaussian free field is actually just a random Schwarz distribution rather than a pointwise defined function. So now the Liouville field on the sphere is defined as follows. So we consider this probability measure, which is the probability measure on the Schwarz distribution on the sphere corresponding to this Gaussian free field. And then this measure, it defines the measure on the product space. So here, this DC is just the big measure, and this Q is a constant depending on gamma. And then the Liouville field on the sphere is simply the push forward of this measure on this product space to this Schwarz distribution space by this additive function. So this is the definition of a Liouville field on the sphere. Okay, and so here are some more details on the Gaussian free field. So here the Laplacian operator corresponding to the spherical metric is defined as follows. And this delta is the usual Euclidean Laplacian operator. And now we can define the distribution energy as this gradient square. And then by the integration by parts, we have this formula. And here, this volume is the volume corresponding to the spherical metric. So then this Gaussian free field has a following explicit construction. So here, because of this formula, we know that the Laplacian operator has positive eigenvalues, except 0, which has eigenfunction constant. And then we consider all the eigenfunctions which are not constant. And then we just taking this sum. So here are a few comments. First, this sum is converged almost surely in the Schwarz distribution space. And more precisely, it's actually converged in the negative indexed subdiv space. And I mentioned that the green function of the Laplacian operator is the covariance of this Gaussian free field. The precise meaning is the following. So we have to take two smooth test functions, and then this covariance of these two test functions is given by this. So I will not give the precise formula for the green function, but I will just say that the green function is equal to minus log x minus y plus a smooth function. So here I have normalized my Laplacian operator to have a 2 pi here, so there's no 2 pi here. Finally, Gaussian free field can be defined similarly on any remaining manifold. Okay, so so now let me define the so-called Liouville quantum gravity. So first, I want to define the random geometry corresponding to the Gaussian free field. So suppose this H is the Gaussian free field defined in the last slides, and then the random area corresponding to the Gaussian free field is defined formally as this. And so since this Gaussian free field is only a Schwarz distribution, this definition doesn't make sense rigorously. So in order to give a precise definition, we need a regularization and a normalization procedure. So here, this H epsilon x is the circle average of the Gaussian free field, which happen to be a continuous function. And then after this normalization, we can show that this limit exists in probability. And this random measure is a so-called Gaussian manipulative calculus of this Gaussian free field. And we know that this limit is non-trivial if and only if gamma is between 0 and 2. So we can also define the random metric associated with Gaussian free field. And this is achieved by these two groups of people last year. They were able to construct a random distance function out of the Gaussian free field by a similar regularization and normalization procedure. But this one is much more difficult than the random measure. And you can see the difficulty between the gap of these two work. So today I will not give any details about this random metric, but I will just say one fact, which is this random metric is the deterministic function of the random area. Okay, so now let me define the Liouville quantum gravity associated with the quantum Liouville theory. So here, suppose this X is a sample from this Liouville field measure. Namely, so we sample this Gaussian free field and this constant according to this measure, and then we just add them up. So then the Liouville measure is defined using this Gaussian multiplicative calculus. So here it is very similar to this guy, but there are some simple twists. And this metric is just defined by the Liouville measure in the same way as how this metric is defined in Gaussian free field sense. So at this point, you might wonder that, so it seems that this Gaussian free field is already a very nice object. And this metric and measure are defined in a very natural way. So why do we bother to consider this funny infinite measure and define the area this way? So one reason is because, so here, for example, in the definition of this measure, we have chosen to consider the regularization to be the Euclidean circle. But this Gaussian free field is actually intrinsic to the spherical metric. And these two quantities, for example, this volume measure and this radius, they are intrinsic geometric quantities to the spherical metric. So in this sense, this is more natural. And more importantly, this one gives the right scaling limit of random parameter maps, which corresponding to the random geometry physics considered in quantum gravity. So let me start by consider the pure gravity case. So according to Polyakov's prediction, the 2D pure quantum gravity is corresponding to the gamma LQG with the central charge given by this magic number 26. And here, if we solve this equation, we find that gamma equal to this number square root of a3. And since we have a rigorous definition of Liouville quantum gravity, we can make sense of this conjecture precisely. So here we consider a uniform sample of a triangulation with n vertices, and this can be thought of as a discrete version of this 2D pure quantum gravity, because pure quantum gravity just means uniform random geometry. And we assume every face is equilateral triangle so that this is a Riemannian manifold. And then we can recall this uniformization theorem and use conformal embedding to embed it to the unit sphere. And this conformal embedding will naturally push forward a random measure and a random distance function on this sphere. So here the triangulation is an example of the so-called planar map. And in particular, a triangulation is a planar map where the face degree equal to 3. But we can also define other types of maps. So this is a precise conjecture of Polyakov's prediction on this quantum gravity and its relation to the Liouville theory. So we set gamma to be this number, and then after proper scaling, this discrete random measure and metric on the sphere, they should converge in the scaling limit to this random measure and random distance function defined in the Liouville theory, conditioning on the total area to be 1. Because in the discrete, we have fixed the total number of vertices to be n. And I also want to mention that, so in the sphere case, we have to pick 3 points in order to fix the conformal embedding, but I don't want to go to the detail of this point. This can be made very precise. Okay, and there's also a notion of universality in these kind of scaling limit conjectures for random parameter maps. So one kind of universality is over the type of maps. So for example, we have considered triangulation, but we can also consider other type of planar maps. And another, to me, more interesting universality is over discrete conformal embeddings. So in this picture, we have just used the uniformization theorem from differential geometry to embed this triangulation into the sphere. But actually, there are some other variants of this conformal embeddings in the discrete, which in the continuous should also supposed to converge to this continuum conformal embedding. And here are a few examples. So last year, Nina Holden and myself showed that this conjecture holds under the so-called Cady embedding. And so on one hand, our work relies on deep understanding of the metric structure of both this discrete uniform triangulation and the random geometry continuum, thanks to these deep works. But on the other hand, our proof also relies on very particular properties of the embedding, so it doesn't extend to any other embeddings. And this question is still open for any other embeddings. And we can also consider the general 2D quantum gravity coupled with the matter field. And here, a conformal matter in the continuum, it can be described in 2 ways. The first way is a conformal field theory with certain central charge, and the second one is using the SLD. So, but the most relevant to us is discretization, which is simply some 2D statistical physics models. For example, Ising model would corresponding to a conformal field theory of central charge 1/2, and the uniform spanning tree corresponding to central charge equal to -2. And then according to Polyakov's prediction, so the continuum limit of the corresponding to this 2D quantum gravity coupled with conformal matter with this central charge, it's given by this gamma Liouville quantum gravity. And the 2 central charges is related by this magic formula. And in the discrete, this discretization of this quantum gravity coupled with matters would just be given by random parameter maps weighted by the partition function of the corresponding statistical physics models. And for the IC model case, since this central charge is equal to 1/2, if we plug in this formula, we have gamma equal to square root of 3. And for uniform spanning tree, we will have gamma equal to square root of 2. So now with this table, we can make precise conjectures about the quantum gravity for scaling limit of weighted random maps, as in the uniform case. And so far, this conjecture is not proved for any non-uniform random maps. So weaker variance has been proved for many models in many sense. And so you can find more details in Nina Holden's talk. And there's also a pretty comprehensive survey by Green, Holden, and myself. And the related very important question is to understand the LQG metric for gamma not equal to square root of 1/3. So I want to mention that in this case, there's no counterpart of these very deep works on this metric structure. For example, in this pure quantum gravity case, we know that the metric scaling exponent is supposed to be 1/4, but this is not known in general. And I also want to mention that we have throughout our lecture, we have assumed this gamma parameter is between 0 and 2, and this corresponding to the central charge for the Liouville theory is bigger than 25, and the central charge of the matter is smaller than 1. But very recently, people are starting to thinking about the case where the central charge is bigger than 1. And in this case, the Liouville area measure doesn't make sense anymore because the theory of Gaussian multiple chaos doesn't apply. But the Liouville metric still makes sense. And I will refer to the talks by Green and Holden for more details. Okay, so now let me go to the case of torus. So similar to the sphere case, there are some very canonical torus 2D manifold, which are just the flat torus. So here, a flat torus is just given by the by identifying the direct opposite edges of such parallelograms. And then the uniformization theorem for torus says that given any remaining manifold with torus topology, there will be a tau on the upper half plane, so that this abstract remaining manifold is conformally equivalent to this torus flat metric. And similarly, in the sphere case, by the transformation rule, in order to understand quantum Liouville theory on torus, we can only just focus on this flat torus. But there is a very important difference between torus and sphere, which is, so given given tau and tau prime on the upper half plane, so these two flat torus, they are only conformally equivalent if tau and tau prime is related as follows. And this means the torus has a very non-trivial moduli space, which is the space of torus metric modulo conformal equivalence. And from this relation, we know that this modular space for torus is given by the quotient of this upper half plane by the modular group. So here, this group is generated by these two transformations. Okay. So now the quantum Liouville theory on the torus is defined very similar as in the sphere case. So here, since we have flat metric, the Laplacian operator is simply the regular Laplacian operator, and we can define the Gaussian free field similarly. And then we consider this probability measure corresponding to Gaussian free field, and this the big measure on the real line. And then this Liouville field on the torus is also just this push forward of this product measure. And we can also similarly define the random geometry corresponding to quantum Liouville theory, which is the gamma Liouville quantum gravity. Okay. So, and this is the way to define the Liouville field on a general remaining manifold. So here we still consider this similar product measure with this Gaussian free field as and the big measure, and then we need to weight it by this term. So here, this Kg is the so-called scalar curvature of the manifold. And since both the unit sphere and the torus, they have constant curvature, you can check very easily that this term is equal to 2qc in a sphere case and just 0 in a torus case. And that's just consistent with our definition of the in the particular case of sphere and torus. So in physics, the quantum Liouville theory was defined as a quantum field theory with this so-called Liouville action. And So the way we define the Liouville field is just the probabilistic realization of this path integral formulation. So here, the correspondence is that this product measure is actually corresponding to this term, and this volume is corresponding to this total area measure of this Gaussian molecular chaos. And then this Liouville action will simply by this reweighting of this Liouville measure. And this approach was first considered in the sphere case by David Companion, Joseph Vargas, and then generalized to other services. Okay, so now let me discuss the scaling limit to random prime maps on torus. So similar to the sphere case, in a pure quantum gravity case, it is modeled by the uniform triangulation of n vertices with torus topology. And we also assume that every face is equilateral triangle. And then, but in this case, the torus has to be conformally embedded to some flat torus with a random moduli. And this will also induce the area measure and the distance function on this random torus. Then the scaling limit conjecture is very similar to the sphere case. So first of all, but we need to add that this random moduli, it will converge in law to some random variable on this moduli space of torus. And then this measure and the distance function will converge to this Liouville quantum gravity corresponding to torus. So in my opinion, this conjecture itself is not much more difficult than the sphere case. But what is very surprising to me is that there is also a conjecture about the law of this random moduli. And this is actually given by a very simple formula. So this formula remains very mysterious to me. So for now, I can only say that this formula is related to this magic number 26, but I cannot say more than that. So, and there are also some similar conjectures in the case of quantum gravity coupled with conformal matter field. So here, a conformal matter field of a central charge CM is, can be defined similarly as in the Liouville theory. It's basically a random function on the Riemann manifold. And this measure is related as follows under this conformal definition. And then the partition function of this matter field is defined by the total mass of this measure. And then when this manifold has torus topology, because of this identity, this normalized partition function, it is actually just a function of the conformal class on torus, which is the moduli space. And in general, this measure corresponding to the conformal matter field, it might not make mathematical sense, but this function usually does. And the corresponding conjecture for the random moduli on quantum gravity of torus is just simply the reweighting of this formula in the pure gravity case by this normalized partition function. And of course, this is also open question from the random prime map point of view. So I want to conclude my discussion on this random geometry part by saying that quantum gravity also induce very natural measures on the moduli space of higher genus surfaces. And the quantum gravity intuition, it motivated a very deep relations between the integration over moduli space, enumerative algebraic geometry, and integrable system. Okay, so the remaining of my talk will be devoted to the quantum Liouville theory as a conformal field theory. So in this perspective, the most important quantity we want to consider is the so-called correlation function of the quantum Liouville theory. And on the sphere, it is defined as follows. Okay. So here, although this X as a perturbation of the Gaussian free field, it does not define pointwise, but this total measure, it can be thought of as a shift of this Liouville measure by this Gaussian theorem. This can make perfect sense. And we have to include this so-called cosmological constant because that will ensure that this correlation function is finite for non-trivial range of parameters. And we can also define correlation function on torus in a similar way. So, but here we need to involve this moduli parameter because torus has more than one conformal structures. And the key property of quantum Liouville theory as a conformal field theory is the following. On the sphere, it says that if we have these points related by Mobius transform, then the correlation function at these different points, they are simply related by a simple factor. And similarly, if these two moduli, they just related by the modular group, then their correlation function is also related by a simple factor. And to see this point, we can think about the three-point sphere correlation function. First of all, so this is the general condition for the boundness of the correlation function. So here, we have to make every alpha to be smaller than q, and the total sum of this alpha is bigger than the Euler characteristic of the surface times q. And in the sphere case, the Euler characteristic is equal to 2. And if you plug in these two conditions, that means we need at least 3 alpha values in order to have a finite correlation function. And so because of this transformation rules of the of the correlation function, and also because that on the sphere, any 3 points are related by Mobius transform, we can see that this correlation function can be factorized as some very simple prefactor depends on the points, and some function only depends on alpha 1, alpha 2, and alpha 3. And this function is a so-called structural constant of the quantum Liouville theory. And in a very remarkable paper by Kupani, Rose, and Vargas, they showed that this correlation function has this very explicit formula. So, and this is a very deep fact about Gaussian multiplicative calculus, because if we look at the definition of this correlation function, the only non-trivial part is coming from here. Other than that, they are just Gaussian measures. Okay, and this formula is called the DUZZ formula because it is previously predicted in physics by DUZZ. So as I mentioned earlier, Balaev and Polyakov and Zamolodchikov, they were trying to compute the correlation function of the Liouville theory, and they realized that 2D local conformal symmetries, it implies very strong algebraic constraints on all 2D conformal field theory. For example, we have the so-called operator product expansion. So here on the left-hand side, we have this exponential functions at 2 points, z and 0, where z is very close to 0. And on the left-hand side, it is a summation over only at 1 point. And here, so both of these higher order terms and this exponent, they are some universal quantities which are hosts for OCFT. And the only special data for any particular CFT is this set that you are summing over these formulas and these coefficients. Okay, and from here, we can say that this gives a mechanism to reduce from a n point to n minus 1 point by applying this mechanism. And so the so-called conformal bootstrap for 2D CFT is the algorithm to compute all the correlation functions in terms of this spec and this 3-point function following this OP procedure. And for the Liouville, for the quantum Liouville theory, the basic input is given by these two. The 3-point function is simply this DUZZ formula in the previous slides, and this set is given by Q plus IR. So the quantum Liouville theory is a primary example of conformal field theory with a continuum spectrum. And many of these conformal matter field in quantum gravity context, they only have a finite spectrum. The most famous example is just this isomodel. And so I want to mention that the reasoning of this conformal bootstrap in the previous slides is very hard to make sense probabilistically, because this measure doesn't really make sense, since this piece actually belongs to this complex numbers. But the output of the conformal bootstrap are some precise conjectures on the correlation functions of the quantum Liouville theory. So here is the example of conformal bootstrap applied to the 4-point correlation function on the sphere. So here, this is the 4-point correlation function applied to these 4 points. And the prediction says that it equals to this integral. So you can see this DOGD formula coming from this OPE exponent. Coming from this DOGD formula, and this function here, this is explicit power series coming from these dot terms. And this power series is a so-called conformal block. And this is universal for all CFTs with the same central charge. And this power series was conjectured to converge in the single disk. And the conjecture would be that as long as this 4-point correlation function is finite, this formula should hold. And this is, and mathematically, this is another deep statement about Gaussian multiplicative case. So in a very recent paper by Guglielmo, Capani, Jose, and Vargas, they showed that when gamma is between 0 and square root of 2, the conformal bootstrap holds. And so they managed to prove it by making sense of the OPE procedure when gamma is between 0 and square root of 2. And this idea extends to general endpoints on both sphere and torus. And then a very natural question is to prove the conformal bootstrap for the case gamma between square root of 2 and 2. So I want to say that this GKLV approach is very robust to extend to endpoints on torus and sphere, but it has very crucial obstruction for this range. But on the other hand, most of the interesting values of gamma from the quantum gravity point of view belong to this range. So in my talk, I have mentioned this square root of a third from the pure gravity and the Ising model corresponding to square root of 3, and the uniform spanning tree corresponding to square root of 2. And yeah, so all these values are actually belong to this range. And so this is not just some standard open question, but I think it's very interesting. And the more open question would be C, DOGD formula and the conformal bootstrap from the scaling limit of random paradigmatic point of view. Okay, so here is another example of the conformal bootstrap applying to torus. And here we need to have this torus parameter. And this function H is the so-called one-point torus conformal block. So in the torus case, we only need one alpha to have some correlation functions. So this is the simplest conformal bootstrap equation of torus. And this Q is the so-called modular parameter of the torus on the unit disk. And the working progress of GKRV extending their approach to the sphere would show that this conformal bootstrap holds for torus also in this range. So here, both this conformal block on the sphere and on the torus, there are some formal power series defined by the so-called Virasoro algebra, which is the symmetry algebra of general 2D CFTs. And the series coefficient, they can be computed recursively. So for some very special parameters, this conformal block, they have some integral representation. And this is usually good enough for many conformal field theory coming from the matter field of quantum gravity, such as the Ising model. But for the Liouville case, we have seen that all these parameters here has to be generic. So, and in this general case, conformal block is a quite complicated object. And very important aspect of conformal block is this relation to the gauge theory. So in 2009, AGT, they discovered a correspondence between the quantum Liouville theory and certain four-dimensional supersymmetric gauge theory. And in particular, the conformal block, they actually corresponding to the so-called instanton partition function computed by Nekrasov. And this is one example of this AGT correspondence applied to this one-point torus case. So I will not elaborate on this formula, but I will just say that this this is the power series corresponding to the Liouville conformal block, and here on the other side, so you have some summation over these Young diagrams, and this summation is a so-called Nekrasov partition function. And this is my last theorem to present. So in a very recent work, so Gaussian, Remy, Eason, and myself, we gave a GMC representation of the one-point torus block. More precisely, we consider this expectation. So here, this H tau is simply the Gaussian free field on the torus restricted to the interval. And this random measure is the Gaussian multiplicity calculus. And then these two functions are some explicit function that I will not give the detail. And then we can define this concrete function when this parameter Q is real. So we have shown that this function admits a analytic continuation around Q belong to 0 and 1, including the origin, which means that this guy give a power series. And we also show that this power series is actually the same as the one given by the conformal block, which is the one here. So to me, this is another interesting fact about Gaussian multiplicity calculus. And as a corollary of our proof, we showed that for gamma between 0 and 2, this series of conformal block, it converges when Q is smaller than 1 over square root 2. And this number 1 over square root 2 is mainly due to some current technical constraint. So the correct value should just be Q smaller than 1. And the approach by GKRV, I think they were able to show that this is true, but for gamma between 0 and square root of 2. And they have to assume it is only hold almost everywhere for P, not for every P. So this is a difference between our approach. And so in a working progress, we are trying to show that this modular group, it acts on the linear span of this probabilistic definition of conformal block. And once this is shown, the fact that this domain, it covers the fundamental domain of the modular group, this will imply that this conformal block actually converges for every Q smaller than 1. So, and I also want to mention that this GKRV approach, it doesn't extend to even gamma equal to square root of 2 by continuity because of the essential obstruction. But if we combine their approach and our work, we can say that the conformal bootstrap holds for gamma equal to square root of 2. And the future goal of our program is to extend this work in general cases, including the four-point sphere. Okay, so this is pretty much what I want to say. And here is a reminder of a few open questions. And thank you for your attention.
Okay, thank you very much. Live, could you unmute everyone for a second so that we could applaud Xin Sun? Okay, I don't have a response from Live, so maybe you could use reactions. Live, could you unmute everyone for applause for a minute or two?
Everybody's unmuted. Thank you.
Okay, so I'm looking at chat and I don't see any questions, but let me ask a question myself. You see, I'm an outsider, but I'm a little bit more familiar with SLE. And so, you know, that's by now already a sort of classical topic.
Yeah.
But, you know, what I know about SLE is that it works only for a certain range of parameters. And there are certain crucial values of the parameters when something special happens to SLE.
Yeah, right.
It's a piano curve, just a very simple curve in some range. Then it starts to cross itself, and in the end, it becomes a space-filling curve. So the question is, are there any special values of the parameters in your talk that somehow correspond to those more classical special parameters in SLE?
So I think, yeah, this is a very good question. So in my talk, there are actually two perspectives. One perspective is this random geometry. And in this perspective, so I didn't mention any proofs, but if we go to the proofs, we have to use this perspective. And we can see that in this perspective, we need to use various important couplings between SLE and linear quantum gravity. And so whatever special value corresponding to SLE will give you some special value corresponding to this LQG. And so far, most of the important values of this SLE, they will give important values in LQG where gamma is between square root of 2 and 2. And that's a range where this so-called conformal bootstrap is not proved.
Okay. Okay, so there's a question actually. Can your findings be generalized to any Riemannian manifold from Andre's?
So conceptually, it can be, I mean, so you can formulate similar conjectures in general Riemann manifold. But so the thing is that for higher genus Riemann surface, it's even a very active topic in just the deterministic geometry. So the technicality would grow exponentially once you go to higher genus surfaces, because the modernized space of higher genus surfaces is very complicated. But on the other hand, if you only care about theorems like this, so let me try to find. Yeah, so suppose you want to consider conjectures like this, where you do not care about any formulas, then I think for higher genus, it's not so much difficult than the sphere case. It's similar to say that any manifold is like locally, it's a Euclidean manifold. So once you know the simply connected case, it shouldn't be too hard to generalize to a general case. But what is more interesting is that once you consider the modernized space, you have these very nice measures. And these very nice measures, they are playing a very important role in mathematics.
Okay, so I have another question.
Mm-hmm.
You know, one of the terms that you used in your talk is quantum gravity. Over and over again, but one of the best known current research directions in physics is the string theory,
yes,
which makes this attempt to somehow unify quantum theory and gravitation. So it's a very general question. Is there any relationship between the two?
Yes, so you can see that in my slides. So this is a mathematical translation of what quantum gravity means. And you can see in this corner that they have this string theory. So basically, so this paper of Polakov is called Quantum Geometry of Bosonic String Theory. So, in string theory, there's a very important statement saying that bosonic string theory has critical dimension 26. And the precise meaning of that statement is actually this. So there's a very close relation between string theory and quantum.
So is this 26 like the famous 26 of
this
string
is the
theory
most famous, right.
Because you know it's even in popular science, like 26 dimensions
so
and so on, right?
Basically, so this is a paper discovering that the string theory in the bosonic string theory should have dimension 26, and then later some other people realized that if you introduce a mechanism called supersymmetry, then you can reduce this dimension to 11. So then people start to look at super symmetric string theory and I think so basically that's the story.
But in your talk, that 26 is not reduced to 11 by any mathematical.
Yeah, because I didn't consider supersymmetry. So once you consider supersymmetry, it is more solvable, but it is not a probabilistic measure anymore, even not positive.
Oh, it's not even positive. Oh, I see.
It's not even a real number, I think. It's just some formulas.
Oh, I see. Okay. Well, if there are no more questions, well, we already applauded. So let me just say that I enjoyed the talk very much, and I hope that everybody else enjoyed it as well. And thank you very much. And congratulations once again on your award.
Thank you very much, Chris.